Good afternoon. Welcome. Distinguished guests, faculty, students, research, welcome to this special Academia Sinica lectures. It is a profound honor to gather here today as we are standing at the threshold of a new era in quantum computations. My name is Chong-Ting Ki. I'm researcher at the Institute of Physics and Research Center for Critical Issues. I'm thrilled to be your moderator today for today's lectures. Before we starting our exciting lecture today, let's first welcome President Liao to give us an opening remark for today's lecture.
Good afternoon, ladies and gentlemen. It's my great pleasure and honor to welcome you to this Academia Sinica lecture. And our lecturer today is John Martinis, who is Nobel Laureate, freshly awarded Nobel Laureate just a few months ago. John and Academia Sinica has very close relations, and it all started in, if I remember correctly, 2021. When we contacted John after his service at Google, and then I paid a visit to John's house in Santa Barbara. So we had a very nice conversation in his beautiful home and started a collaboration between Academia Sinica and John Martinis' team. And for 2 years, John served as our consultant for our quantum computing team. And he has held weekly meetings with our researchers. And almost every time is run to every single details. He's that kind of scientist, and not just a scientist, but also a very good engineer. So he will tell you to make quantum computing a real possibility, you have to perfect your physics. But more importantly, you need to perfect your engineering. Okay? So it is our great honor to have John to give his second lecture in Academia Sinica, because just a couple years ago, he was here in the same room giving the same lecture, Academia Sinica. So it's our great pleasure and honor to welcome John back to give this lecture.
Okay, thanks to President Liao. As he mentioned, John just awarded from Nobel Prize in Physics a few months back from the Royal Swedish Academy of Science. And I would say John is an exceptional physicist. He can actually work on the quantum tunneling property from macroscopic junctions, but he can also work with us on entire morning to talk about how to reduce the noise of the system by tapping your ground properly and make sure we can understand every detail of the noise of our system. That's exceptional, helpful with very engineered mindset from him. We are also very honored to collaborate with him in fabrication of superconducting qubits. That's actually one of the great achievements in past few years. We work together to industrialize this fabrication process. His work from previous providing circuitry to behave quantumly to the first ever demonstration of quantum supremacy in 2019. He has consistently pushing the boundary of this field. Today he joined us to discuss the next great leap in industrial revolution of quantum computing. Please join me to welcome a true visionary and engineered physicist of 2025 Nobel Laureate, Dr. John Martinis.
Thank you very much for this warm invitation to visit. We've had a very good visit last couple days, and thank you all for coming out and seeing this presentation today. I'm really impressed so many people in Taiwan are interested in quantum and quantum computing. Quantum computers are a real big promise to be able to compute for certain problems much more powerfully than what we can do with classical computers. And of course, classical computers are an everyday part of our lives now. And if we can use the physics of quantum to compute more powerfully, this is going to make a really big change in what we can do with technology. It's a very exciting field. Many, many people around the world are working on this. I was very fortunate to start my trek on this in the 1980s, even before the word qubit was invented. This is why I talk about prehistoric quantum bits. And it's been a really wonderful time. And it's just very exciting, all the things that are happening. So what I'm going to do today is first talk about what turned out to be my thesis experiment with John Clark and, of course, with Michel Devereux, looking at these macroscopic quantum effects, tunneling and energy level quantization, that kind of put the idea that we could make electrical atoms, if you like. And that will be kind of the 1980s. And then in the next part of the talk, I'll discuss quantum computation and give you a brief overview of what that's about and why we're interested in it. And that kind of covers some of the late 1980s, 1990s. And then in the intermediate years, I and many other people around the world have been working to develop these qubits. And I'll briefly describe what we did in 2019 on the quantum supremacy experiment, where we showed that a quantum computer could be powerful. This is for a mathematical problem, but it showed that, there's really something here and we want to take advantage of it. And then for the last part of the talk, I'm going to discuss what we're doing in the future and how we're going to take this technology, which has really been shown in the lab to work very well, and to further improve it into, I think, hopefully making this manufacturable, and then build a useful quantum computer that can solve real-world problems and be a benefit to society. So here's what I did for my thesis experiment. Here's quantum bits in the quantum supremacy experiment. Now, I want to first talk about what we were trying to do here in the 1980s. And when you're a physicist, one of the most amazing classes you take as a physics student is quantum mechanics, because it describes the world of the small, of fundamental particles like electrons or photons, describes how atoms work, describes how molecules bind, really some of the fundamental laws of how physics works of the small, and you learn how that happens and the mathematics of how that happens. What's, I think, interesting about this is that nature allows you to use quantum mechanics naturally, say with the atoms in the periodic table. And because of the intricacies of quantum mechanics, all of these atoms in the periodic table have unique characteristics that you can take advantage of, and of course build nice molecules and other materials, other things that are so important in the modern world. What in the end we were trying to do is to show new kinds of atoms, macroscopic atoms, artificial atoms, that are no longer just built out of electrons and protons and neutrons, atoms, but it's actually built out of electrical circuits. And our basic elements here, if you look at the circuits, are capacitors, inductors, transmission lines, things called Josephson junctions. And instead of building the circuits out of normal matter that we think about, we can build circuits out of electronics. And this is really interesting because if you think about how modern computing works, say your cell phone, this is an electrical circuit. And using the idea that you can build quantum systems out of electrical circuits, naturally leads you to do more powerful things, like building a quantum computer. So it's a really interesting way to think about building these novel quantum devices. So macroscopic atoms, new macroscopic atoms, different than the quantum mechanics of the normal atoms that we're used to thinking about. Now here's a picture of the device I made in graduate school. I actually machined this part myself. So it's actually very carefully designed. And what we have here in the bottom left, bottom left, oh, don't do that. Here is the chip. This is the chip. It's about 1 centimeter in size. And what we're having here is the currents flowing through this chip, and the voltage across the chip is our quantum system. And it's of a macroscopic number of electrons and Cooper pairs flowing through that device. And we see the quantum mechanics of electrical circuits. Now this quantum chip, something you can see, it's macroscopic, is connected to this other experiment here. And let me explain a little bit about the experiment. What we're trying to do is look at the quantum mechanics of an electrical circuit. It operates at about a microwave frequency of your cell phones, about 5 gigahertz, operated at very low temperatures. But to see the fragile quantum behavior of the circuit, you have to cool it down, but you have to get rid of all the noise from the rest of the world that can get into your experiment. And because in the end, you have to connect this up to room temperature, to some electronics, to control the experiment. Now, when we first tried this experiment, testing out if it would work okay, it was an absolute disaster. Didn't make any sense at all. We took data, didn't make sense. And it was because all this external noise was getting into the experiment. So we had to think very carefully about how to microwave engineer the device, put in filters, make sure we shielded out all the radiation and noise, thermal noise getting into the device. And the essential idea here was kind of illustrated in this particular cross-section here, how we mounted the device. That's from here to here in this chip mount here. And the big idea here is the wires that are connecting the chip down to the end with the microwave connectors up into room temperature where we're measuring it. That has to contain filters. And this filter in this case is made with copper powder, small diameter. And what it means is that if you have any noise coming in for the left, it gets absorbed by the copper powder before it gets to the chip. So the chip sees an absolutely clean microwave environment looking out into it. And for those of you microwave engineers, you see that this is a coaxial line, so it looks like a very nice impedance of about 80 ohms, so that the chip is looking into the rest of the world is in a really good environment. So here, filtering was very important. Microwave engineering was important. We used to take our devices, go to the astronomy department, use their microwave equipment to make sure we understood what was going on. And it was that kind of engineering that allowed us to build the experiment. Now, what you see here is the device down here. It's connected up to one filter and then goes down to a second filter because we're really careful about doing everything. And then a secondary filter for radio frequency, about 100 megahertz to 500 megahertz or so. And by doing that, we can make sure that the junction is really in a good quantum mechanical condition. Then we have a little connector right here, where we can put in microwaves, and that injects microwaves down into the line, and that excites the qubit chip in a way I'll describe in a few minutes. So this is the basic idea of what we're doing. Now, the way this experiment works is that we have a superconducting wire, superconducting Josephson junction, and superconducting behaves such that as you put current through the device, there's 0 voltage across the device. That defines a superconductor. It's a special phase of matter with 0 voltage. However, when you make this tunnel junction without a superconductivity, you can only put so much current through the device. If you start putting more current through the device than about 5 or 10 microamps, if it's designed carefully then it's no longer going to look like a superconductor. It kind of breaks the superconductivity, and you see a voltage appear across the device. And what we're going to do in the experiment is we put the current just below the critical current, and then every once in a while it'll fluctuate from the 0 voltage state to the voltage state, either by thermal noise at high temperatures or quantum mechanics, quantum tunneling, some kind of quantum phenomenon. It can go to the voltage state a little bit before it's supposed to, ideally. And that's the physics we're looking at. This is the physics of an escape rate, escape system. The escape from the 0 voltage state to the voltage state. So the experiment we did here, and I'm just going to show these results. This was the most clear results that you're seeing quantum mechanics of this system. And to explain how this is showing quantum mechanics, let me explain a little bit about energy level quantization in atoms. Okay. If you take a tungsten wire and you put current through that wire, it heats up and you emit light. And that's the kind of light bulbs that have been used for many, many decades now. But when you emit light from a tungsten bulb, it's white light. That means you get light from all spectrum, red, green, blue, everything in between. And it's kind of a continuous spectrum. And that's kind of a classical behavior. However, if you take an atom, let's just take neon as a good example, and you put current through a neon gas, then, as you well know, you see a neon light, it comes out with a particular color. Okay, you've seen neon lights. That color is a very distinct color. It's not white anymore, it's a distinct color. And that's because the electrons in the neon atom only want to oscillate at a certain way, at a certain energy or certain frequency. There's something called energy levels in that atom. Let's say a low energy level, ground state, excited state, and only when the gas goes through, you excite it, and then it decays a certain energy, a certain frequency of light that then gives you that very distinctive color. And all atoms have their own distinctive set of colors. So this is actually when quantum mechanics was discovered and understood, starting to be understood. This was very surprising in the beginning. Why do you have these distinctive frequencies coming out? And it's because the light comes out in quanta, in certain energies. And that's what you look for to absolutely make sure you see quantum mechanical behavior. So what happened here is we measured the escape rate, which is this gamma, when there was no microwave power versus current here. And then what we did is we measured when we put on some microwave power. In this case, it was 2 gigahertz. So if you add some energy into the system by pushing it with microwaves, you expect the escape rate to go out of the 0 voltage state to the voltage state to be enhanced. You're pumping energy in it. And that's what you see. This is the change in escape rate, gamma, with power minus with no power. And you see an enhancement here. But what happens is it's not just a continuous enhancement, but there's 3 distinct peaks here that you see coming from this microwave frequency here. And these distinct peaks turned out to be basically the colors that I was talking about for the neon light. So what's going on in a little bit more detail is as we change the current through the device and we get closer and closer to the critical current, this potential barrier that this system lives in gets smaller and smaller. And that's why when that barrier goes to 0, that's why you go to the normal metal state eventually. But what happens is it goes from a relatively shallow well to a steep well, and it changes the frequency of the qubits going from here to here. And what happens is this particular peak here is a transition from the ground state of the system to what we call the first excited state. And then the second peak here is the first excited state to the second excited state. And this very washed out peak here is the second excited state to the third excited state. So by seeing these peaks here, you have a very clear, unambiguous observation that there are energy levels here. If it was a classical system like normal electronics, you would see kind of a washed out signal here. And that's what we see at high temperatures. But quantum mechanics, we see these energy levels. So, that's nice. You understand, you see quantum mechanics. In the end, if you want to describe how this system works, this electrical system, you have to use this energy level language to do that. So this was very nice at the time. We showed that you can see quantum mechanics. It's how it's obeyed. It has these energy levels. And then what happened over the years is people figured out how to use these energy levels, both of this and regular quantum systems from atoms, in order to do quantum computation. And that's kind of the next stage of my talk here, is to discuss kind of how these quantum states work and how it gives you computation. So now let's go to a little detour here to talk about the theory behind quantum computation. When you do classical computation, you know that your classical states are defined either as a 0 or 1, which could be, let's say, no voltage on a capacitor or some big voltage across the capacitor, okay? And it could be 0 or 1, and you put together a bunch of zeros or ones to make a word to encode information or numbers or whatever you want to do. When you can encode information also whether you're in this quantum state or not, whether you're in the ground state 0 or the excited state 1, as I just showed you. And of course, this can be done for regular atoms too. But what's different about quantum mechanics is that you can be kind of in a mixture of both 0 and 1 at the same time. Not quantum physics, quantum mechanics allow that, whereas in classical bits, it's either a 0 or a 1. Here, you can kind of put them in both at the same time. And the way we write that quantum mechanically is we have this notation, which is a bracket notation, where we have a 0 state here, a quantum 0 state, quantum 1 state, and we have a plus sign saying that it's the superposition of the two. Now, normally with classical logic, if you study Boolean logic and you have a bit of information, you can either do nothing to the bit, so 0 goes 0 and 1 goes to 1 over time, or you can do a not operation where a 0 goes to 1 and 1 goes to 0. In quantum physics, you actually have an increased instruction set over what you have with classical physics. You still have do nothing or a not gate, but you can also take a 0 state and make it go to 0 plus 1. That's a new instruction that you have with quantum physics, and that enables you to design much more complicated algorithms, as I'll talk about in the next few minutes. Now, the reason why this is very useful, and this is the case of just a single bit, if you put it into the 0 plus 1 state, take that state and run it through your quantum computer, at the end, you get an answer of what your algorithm did for the case of 0 and what your algorithm did for the case of 1. And you've done some kind of parallel kind of computation, if you like, for 0 and 1. Now, parallel, it's 2 states here, which is nice. A parallel operation of factor of 2, that's nice. Not anything sounds very useful, but with the quantum mechanics allows you to do, having this kind of bigger instruction set, you can do something like that. Now, once you have 2 qubits, You can then have 0 and 1 in each qubit so that the total number of states that you're computing now is 4, 0, 0, 0, 1, 1, 0, and 1, 1. And you see by adding 1 qubit, you've doubled the number of states that you can parallel compute. So if you have 3 qubits, it's going to be 8 states, 4 qubits, 16, 5, 32, and you see the amount of parallel computation that you're doing here is growing very rapidly, growing exponentially. And that's where the potential power of the quantum computer becomes evident. So by the time you get to n equal 50, which is what we're going to talk about here shortly, 2 to the 50 is a big number, about 10 to the 16. And if you can do parallel computation in that way, you actually can do something that challenges a regular classical supercomputer to do, that kind of parallel processing. And then at n equal 300, 2 to the 300 is a number bigger than the number of atoms in the universe. And clearly at that point, you're doing something very interesting, very powerful, and that motivates you to make very big systems. Now, what I want to say is you have to be very careful about this, because when you run a quantum computer and you run the algorithm, at the end you have to measure that. And that just gets you a classical 0 or 1 out of all your quantum bits. So then you don't have 2 to the 50 or 2 to the 300 states, you just have n. You have 50 or 300 pieces of information. And this measurement, fundamental to quantum mechanics, kind of collapses that information if you have a smaller state. And what this means is that when you develop the algorithms, you have to take that into mind in how you develop the algorithms. So it's not like every classical algorithm can then be put into a quantum computer and made faster or better. You really have to think about what happens with measurement and tune up the algorithm properly so that you can take advantage of this. And I'll talk a little bit about that, but it is a limitation of what we can do with it. But there are important cases we can look at. So yeah, let's talk about that. What are the quantum algorithms? What can we do with a quantum computer? Now, the first thing that was realized in about 1990 by Peter Shor was that if you could build a quantum computer, you could actually think about breaking the modern encryption, the RSA standard, which is based on the fact that if you take a big number, if you take 2 prime numbers, multiply them together, you get a bigger number. And that's relatively easy to do. But if you take that big numbers, you want to go backwards to know what the 2 prime numbers is, that's a really hard problem. And classically, that takes a huge amount of effort to do and really can't be done. And the basis that one way is easy and the other way is hard is the basis of modern RSA encryption that we all use for internet security. It's been around for a long time. It's a good algorithm, but quantum mechanically, this is something that people should be able to do. Because of that algorithm, now that people are thinking about building powerful quantum computers, we have to start worrying about that. And people have developed quantum-resistant protocols. So the internet is going to be safe. People are just going to have to move to these a little bit more complicated algorithms to make sure it's okay to protect themselves with a quantum computer. I'm more interested in using a quantum computer to help humanity, obviously. And a big application that I particularly like as a physicist is quantum chemistry and quantum materials. And the same reason why a quantum computer can be powerful also means if you really try to understand how an atom works or a molecule works in great detail, big molecule works, you can run that on a classical computer, but kind of the state space blows up and it gets really hard to compute. And because of that, people use classical computers to design molecules, but you can only do it to a certain size. Now, it turns out it's taken a while, but scientists now know how to map a quantum computer to the quantum chemistry problem. And they have some nice ways to do that. Lots of interesting things going there. And in the end, you can use a quantum computer to solve quantum chemistry, quantum materials problems. How does a molecule bind? You make a semiconductor device. You can maybe look at some of the detailed quantum mechanics of how that works. So there's many technical applications. There are known algorithms. I would say, although there's simple things you can do, in the end, you're going to need a big quantum computer to do that. Something like maybe 100,000 to 101 million qubits, in large part because you have to do error correction. The qubits naturally have noise and errors, and you have to correct for that. But that, to me, is a really, really interesting application. Also, modern AI is now trying to solve these kind of problems, and I think the combination of quantum computing and modern AI can really make a big, important improvements in the way we do quantum materials. The other thing people often talk about are optimization and machine learning. The classic example is the traveling salesman, where you have a series of cities and you want to find the minimum path length. This actually is kind of a nice example of optimization. It's actually, people have really good algorithms for solving this. But there's plenty of algorithms where you want to find some kind of optimal or near optimal solution, where many quantum physicists are looking at those applications. And there's much research on it. What's interesting about this is this heuristics approach here, much like deep learning and the large language models that we see today for GPU usage, where people are looking for the solution. We may be able to find the solution that works practically. Maybe there's not a theorem saying why it should be better, but there's really an opportunity there for the quantum computer to make a very large impact, because optimization problems are all around. In terms of how to make that, how to build hardware, it's a very interesting field right now because there's many, many approaches to doing that. I'm talking about superconductors here. People look at individual ions or neutral atoms in some kind of ion or light trap. People doing it with photons. They're looking at semiconductors and the spins of the electrons in there. Diamond, people make annealers. Very, very rich and powerful field. I'm going to focus in on superconductors. The interesting thing is, if you go talk to people on all these different systems, they all say that their system is the best, and we're going to be able to make a quantum computer, and that's really great. I think people are extremely excited. All these different ways of doing it. What I'm going to say is the nice thing about superconductors is that people have made complex systems. It works in all the different ways that you want a quantum computer to work. I would say the big problem with the superconducting quantum computer is scaling it to huge number of qubits. We're going to talk about that at the end. The one thing superconductivity has really going for it is it's pretty fast. It's maybe 1,000 times faster than ions and neutral atoms, which are really doing quite well right now. Very interesting system. I think the speed of the superconductors will mean in the long term they're going to be better because they're faster, and also because the superconductors are made with integrated circuits like we make our chips right now. I think in the long term we'll be able to manufacture and scale that up better. But there's some work to do there. Okay, so let's talk a little bit about superconducting qubits, what a modern superconducting qubit's like. It's a microwave electrical circuit. And what we have here is a picture where there's aluminum almost everywhere. That's kind of the light tan. And then where it's dark is where there's a cut in the aluminum. And what we see here is a typical qubit device. This may be made at UCSB, but it's not untypical, where there's a capacitor formed by this metal electrode here to the ground plane all around it. So that's a capacitor of electrical resonance circuit. there is a Josephson junctions right here that forms an inductor. It's a nonlinear inductor. And basically with that inductor and a capacitor, you form a nonlinear microwave resonance circuit at about 5 gigahertz where we store the information. And given that it's an electrical circuit and not a very complicated resonator at that, about, let's say 70% of the physics of the device can be understood with standard kind of engineering principles used for microwave devices. You can see the device is not that small. It's about 0.2 millimeters across, sometimes a little bit bigger than that. So it's not hard to do with lithography. The Josephson junctions are about 0.1 microns, and that's, again, not hard to do. We see wires coming in from the right and from the bottom, and that's used to control the qubit. And you see that the wires are much smaller than the qubit size, so we can bring them in and control that properly. We also have this structure on the top, which is a secondary microwave resonator, which is used to read out the qubit or read out its state. So macroscopic, easy to control. We can bring in wires. Microwave engineering properties, so we can understand how this works, mostly with electrical engineering concept. And of course, it's built like a computer chip. So the idea is once you know how to build one, then you can just step and repeat that and build many. Of course, there's lots of other engineering like crosstalk you have to worry about. But again, most of that is like classical engineering. So I'm just going to skip forward many years, okay, to when I was working at Google and did the quantum supremacy experiment, published in 2019. This was an experiment that showed powerful computation. So this is the chip. It's actually 2 chips that are bump bonded. You can see on the bottom chip, there's a bunch of wires going into the outside, which we then do to all our control system. There's a chip in the center where we do all our qubits. And the layout is shown on the left here, where the gray cross are the qubits, kind of like what I already showed you. And there's this adjustable coupler circuit that's in the blue that allows the neighboring qubits to either talk to each other or be isolated from each other, so you can turn on and off the interactions. In this particular device, what we did in the quantum supremacy experiment is we basically used the device to generate random numbers, okay, as a mathematical test of the quantum computer. So we basically ran a known but fixed random circuit. We got outputs. And although in the random circuit you think you might get random outputs, some of the numbers are more likely and some of the numbers are less likely due to the quantum mechanics and quantum interference of that. And by running this and sampling the output states we get, we would then compare it to a full quantum computation on a classical computer and see if the answers we got were the likely ones or the not likely ones. And of course, you want to be able to see that it's the likely ones. And by doing this, even though it's a random number generator, it's a very detailed test whether the quantum mechanics is working properly, whether you have errors, whether you have the whole system working properly, not just individual qubits. And although the qubits were not perfect, and only some fraction of the time did we get the right sampling of the random numbers, you can compare the fraction where it worked to what you expected, knowing the known errors, and that all made sense. And what it told us in the end, that you can do this powerful computation and you aren't getting any new physics that are giving you more errors that would then kill a quantum computer. So it really showed that kind of our basic knowledge of how a quantum computer worked would be fine, and it shows you on what would be a very powerful computation. So in this case, there were 53 qubits. So we did this parallel computation on 10 to the 16 states, and things, worked as expected, okay? So this, of course, generated a lot of interest in, the quantum computer was possible. I mean, when I joined Google, I think the very hard-nosed engineers at Google was wondering, well, how could possibly this little physics experiment beat out their big clusters of computers, classical computers? And this experiment showed that indeed the physics allows you to do that. Of course, the next thing we want to do is build a useful quantum computation, useful quantum computer, where you can do something and in the end, benefit society, benefit materials, benefit an optimization problem. And that's where the field is right now. And there's just a lot of interesting physics going on with many different systems to try to figure out how to do that. And with that in mind, what I want to do next, let's talk about this in a little bit more detail, show some pictures. Here in the upper left is the device. Here it's mounted, and you can see we've wire bonded all these to a circuit board, and we just have an array of microwave connectors to bring out the signal. And then here, this chip is buried somewhere in this forest of wires here. We've connected these microwave signals. They have filters and other microwave components, and then goes up to the dilution refrigerator to room temperature, where we have control circuits. We take measurements of the device. And this typical device frequency is 5 gigahertz, kind of like a cell phone frequency. And then we have to go to very low temperatures, 10, 20, 30 millikelvin, so that the thermal noise is way, way smaller than the quantum energy coming from the 5 gigahertz state. So it does involve operating this is a dilution refrigerator machine, which is a little bit complicated, but frankly, you just buy it and fill it up, and you can get this to work in a reasonable way. So, and again, let's talk now about where we're going in the future, and where I see, especially our company Colab, where I think the field is going in with these superconducting qubits. And if you look at the picture of this device, this is 2019 to 2026, what you see is a cryostat with lots of wires, these wires are connected to your qubits. And if you think about that, it's nice that it works, but it looks a little bit like what computers looked in the 1950s or 1960s, where you have individual transistors, which are forming the logic gates, but then you have a mess of wires going all around, connecting it all up. And that's what computers were made like initially, and they worked and showed that you could do useful things with them, and that was all great. But, that's not really what happened, why we have these kind of cell phones right now. And what happened over the course of the years, from early 1960s, say, to the late 1970s, is what the microprocessor and integrated circuits were really developed and perfected, where you put lots of transistors on a circuit, you connected it up with wires, and you were able to minimize that size. And of course, by working on this for many, many years and packaging it better, which, clearly people in Taiwan have been very good at that, you've then got to build really, really powerful computers. And our idea, which is what we need to do in the quantum computing field, is make that transition over to full integrated circuits. Here, the integrated circuit's in the center, tiny, but it's surrounded by all these wires. And here, all the wires on the outside, we need to integrate and make it into a small package, kind of like what's going on here, in order to scale this up better. And that's our goal. So how are we going to do that? Okay, so one part of the solution is that we're going to use advanced fabrication. Right now, these are devices is what is essentially an academic clean room, although people have dedicated clean rooms, and it works pretty good. But what our idea is we really need to go to tool builders like Applied Materials and use the latest semiconductor fabrication tools, which are at 300 millimeters, and use that to build our devices in a more reproducible, build them with quality, build them in a way we can scale them. And as we begin to do this, we think we can improve every process step in doing so. So this is an example. On the right is a 300 millimeter tool from Applied Materials. It's called Endura tool. Very commonly used. People have been using this all the time. I mean, there's probably thousands of these tools in Taiwan, okay? And that's the 300 millimeter tool. And then Applied Materials, this tool is in a big clean room. That's an R&D clean room. And we think we can use an existing kind of R&D kind of clean room and retrofit the tools as needed. And that's good enough for the initial manufacturing and do that right. Obviously, there are many clean rooms around the world who can do some kind of metallization, but you have to develop custom processes to get that to work. So, advanced semiconductor fabrication, what are some of the principles we're doing? This is for maybe some of the audience here who knows more about fabrication. Obviously, Taiwan, they're quite expert at this. There are three main things that we kind of put this into. First of all, right now, when you make these devices all around the world, they're using a process called liftoff. And liftoff is where you take your wafer and you coat it with this photoresist and expose and develop it. And then you evaporate, say, aluminum on top of that. And where the photoresist is gone, the aluminum sticks to the metal. And then you put it in a beaker of acetone, which dissolves the photoresist and lifts off the rest of the metal. Now, for those of you who know about fabrication, this is a really dirty process. And this is what people did maybe in the 50s or 60s. I don't know exactly the history. They did that a long time ago. No one in their right mind does that at your, amazing fabrication facilities you do right now. It's all deposition and etch because you can control it, make clean processes, and do it much better. So, that's what people are doing right now. It works. It's fine for prototyping, but we think the field has to transition. So we've actually built a lift-off-free junction. This is actually a device that was built here in Taiwan with Academia Sinica and ITRI. And what we do is we use an SiO2 as kind of a scaffold. We make a vias into it, and then we clean that out, make a junction, put aluminum on top of that. And what we have here is an aluminum base metal, and then a junction right here that's submicron, going up to aluminum top level. And then we remove all the SiO2, which is very lossy, and then we have a lift-off-free junction. So this works. We had some data. I think we're going to get the paper published soon. But we're trying to do it better than that and working on that processing. And there's some other advantages we think for doing it. So this and other ways to do it, we think we can make much better devices. Another example here, and this is from Applied Materials, is how we deposit our aluminum on a silicon. So when we do aluminum on silicon, the interface between the aluminum and silicon has to be atomically clean, and they can do it so that they can put the silicon in their device, clean off the surface in vacuum, and then you put aluminum on top to a very good interface. That's clean. The other thing they can do is grow the aluminum in a very uniform way. These are basically single crystal aluminum devices, tens of microns across, and then making this very flat will enable us to make more reliable Josephson junctions. So Applied Materials knows how to do this. The last thing we're going to do here is shown here on the right. And instead of having all these wires and coax and SMA connectors that are expensive and frankly unreliable, we're going to do wafer scale integration. And in fact, right now, there's a company in the US called Cerebras who makes AI processors out of a single wafer, 300 millimeter wafer. This has been done. Our density, our electronics is way less complicated. So we think this can be, wafer scaling can be done, but it does involve some work. So what we have here in the blue would be a qubit wafer, maybe about that size, 14 centimeters by 14 centimeters. You then bump bond it to a 300 millimeter wafer, shown in red, and be about that size. And then the wires from the qubit wafer go through the bump bonds and then go through the silicon wafer. And what's amazing is we have some technology ideas here where one end of the silicon wafer can be at very low temperature, the other end can be at this higher temperature, 3 Kelvin. And even though silicon is known as a very good thermal conductor, if you build that right, you can thermally isolate it and make a single wafer to integrate everything together, and then put all of those microwave control electronics on that wafer. And then from 3 Kelvin, you can use something like a copper alloy flex to go to CMOS control electronics at higher temperatures. So all of this, we have a long paper that describes this. All of this, we have an idea on to build it. It looks nice on paper. Of course, we have to build it. And right now, what we're trying to do is find partners to help us manufacture this and to use modern semiconductor manufacturing to both make the chips and also package it and put it together. Have to do wafer scale bump bonding, that's kind of state of the art, but do all these things, and then we feel we can make a much more reliable, much more scalable, get up to millions of qubits that we're going to need. So we're starting very seriously on this project right now. So just kind of as a final slide here, what is this thing going to look like? These are the dilution refrigerators closed up like I showed here. In order to make millions of qubits, you're going to have to place them together. And then there's going to be control electronics connecting to that onto the left here, where you put that. You may have to do some classical GPU kind of processing to do the error correction, but it'll kind of look like a big data center, kind of fitting in this kind of stage kind of room here. And we think, if we get the manufacturing right, we'll be able to build all these components in a reasonable way to make it work well, scale it up, but also have it not cost too much, which of course is very important when you're trying to build computers. So in the end, thank you very much for your attention, and I'd be love to answer questions at this point.